for the invitation. It is a great pleasure to be here and celebrate Jeremy. So I only met Jeremy in October, and I knew of his work, and it's so nice to see that behind this mathematical giant, he's just a really cool guy. So I'm very happy to be here and celebrate him. So the talk is about card shuffling, but you can always think about it as a multi-species exclusion process, and then we're right on theme. So we start with a deck of n cards. Actually, let's do 2 n cards. And if we were to do random transpositions, what we would do is you pick one card uniformly at random with your left hand, and you pick a card uniformly at random independently with the right hand, and you swap them. Okay, that's what Diaconis and Shahshahani studied years ago. Here we're going to do something different. We're trying to have some sort of asymmetric type of situation. So let's say we have the cards that lie on the top and positions, and the cards that lie on the bottom and positions. And what we're going to say is that a card gets picked from the first top end positions with probability, say B over N. I'm going to say that B is a parameter, a fixed parameter between 0 and 1. And the card gets picked from the bottom half with probability 2 minus B over N. Okay, so that's the law. We pick one card according to this probability measure. We pick a card IAD in an IID fashion according to this probability measure, and we swap them. So swap, pick 2 cards IAD from the above measure. And the question I like to study is how many times you need to repeat this process until the deck is well shuffled. And we're going to define everything mathematically soon. Sorry? No, because it's 2n. So you need to multiply here with n.
Yeah, so
It should add to 1. So, but my brain power will exponentially decay during the talk because we're approaching dinner time. So if there are constants missing, bear with me. Good. Sure. So I did the computation before, so I hope perhaps I did it wrong. So how many times? So how many times do we need to repeat this to shuffle well the deck? And so in joint work with Alan Young, who's a PhD student of Lauren Williams at Harvard, we proved that that happens at the inverse analog 2n steps. And again, I'll make the math clear. I'm just trying to tell you what's happening here. Okay, and that's what's called the mixing time of the card shuffle. So obviously, no one would suggest that you shuffle a deck of cards in this fashion. Transpositions up to this day are still the best model we have to understand the way that particles behave in a DNA model situation. So somehow genes organize themselves according to, not exactly transpositions, but this is the closest to what behavior they follow. So this is one of the reasons why we like shuffling with transpositions. And for people who like asymmetric exclusion processes, usually you think of a segment. Here you have the complete graph and you have some sort of asymmetry. There are other versions of asymmetry that one could consider. This is one that you could study. The other ones I don't know how to study. So to set up mathematically this model, I want to first of all make it clear that asymmetric group is what's hidden behind. So when you buy a deck of cards, they come in a specific order. So let's say 1, 2, all the way to 2n, and that corresponds, of course, to the identity element of the symmetric group. Say you're to transpose the top 2 cards. that corresponds to the transposition 1, 2, and so on. So from now on, we will be playing with a symmetric group. And if we are to take two permutations, we will build a transition matrix. So the XY entry of the transition matrix will just capture the probability of moving from XY after one step of your favorite shuffle. This is our favorite shuffle. And so this is an n factorial or 2n factorial by 2n factorial matrix, because you can make x vary and y vary, so you get columns and rows, and you can raise this matrix to the power t and ask, okay, what does the xy entry of p to the t capture? And that is the probability of moving from x to y, but now after t steps. And so the point is that when we send t to infinity, classic Markov chain fact, this will start looking like the uniform measure. Just to define the metric that we usually like to study this with, we will have this notation. So we will put a starting point down here, the power up here, and y there. Because we want to study its convergence with respect to basically the L1 norm or the total variation distance. Actually, let me put it here. So total variation distance. Between the X row of the transition matrix, which is a probability measure, and the uniform measure. So the definition is that 1/2 the L1 norm. Okay, I'm fixated with a symmetric group, but of course you could have a different configuration space. And the mixing time now, so when we ask how many times you need to repeat this to be shuffled well, what does well mean? Well, take an epsilon positive, so you tell me what the error should be, and I should be able to tell you what is the first time such that the total variation distance is less than epsilon. Okay, so of course, if you like different metrics, you can replace this, but usually we like total variation distance. And so now I can write our theorem, and since this is work in progress, we only finished the analysis last week, I will write it in a little bit, not sloppy exact way, but what our theorem says is if you take this many steps and a few more, so smaller order than n log n steps. In fact, I believe it should be just order n. Then the limit of this total variation distance as n goes to infinity should be 0. I could even tell you most likely that this will be exponentially small on whatever you put in front of your window. So I can write something more precise, but because it's not fully written yet, I don't want to commit to it. So this is what this talk is going to be about. Part B is the lower bound. So if you take a few less steps, literal, then this limit will be 1. So you're not shuffled at all. And I think I've said that usually here, we like to take the worst case starting point, but we are in a Cayley graph. We're in a situation where the identity is enough. We can just start the first row of the transition matrix. Otherwise, I would have considered a worst case scenario. Yes, please.
Remember the little of, you don't mean anything small. like
No, 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 no,
zero,
no, 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 no.
Something that kind of
Okay,
growing.
okay, good. You know what?
Hard, but
What I hope we will prove, but you know, the analysis is a little bit daunting. I didn't want to commit to it, but let's say something like this. But there might be a log n here, and I didn't want to commit to it. Whatever, it's fine. It's fine, as long as we
something
understand.
less than but bigger than.
Yes, yes, something, yeah, not anything, not anything. You're right. So the picture that we like to draw whenever we have such a scenario is the following. So let's call this dt. So if you plot dt in terms of time, at time 0, you're really not shuffled. So you are at 1, and you stay at 1 for a long time, and then suddenly you see a drop, and that's what's called the cutoff phenomenon. The definition of cutoff would have taken a limit in terms of c here to give 0, and a limit of c here being 1, and that's how you would define it if you really want to hear it, but this picture should capture it. And in terms of the story of this shuffle, the case b is equal to 1, or b is back to this parameter, Diaconis and Shahshahani that's their seminal work. They use representation theory to analyze non-biased transpositions, random transpositions. B equals 1 means there's no bias at all because the weights are the same. And since we are playing with 2 n cards and not n cards, the mixing time that they had is exactly this, so it should match what I wrote. And they use representation theory to study this, and this is where this is going, but I have oversimplified the idea so that there's almost no representation theory. So how would you prove something like this? And again, I'm focusing on part A because part B really follows their argument. You just look at the number of fixed points, and that's yes.
Slow. Shuffling algorithm. Because you have the constant B.
Yeah. So here is B equals 1. Yeah.
Well, I'm not saying that the result is worse. I'm just saying that the mixing time for the asymmetric shuffling algorithm is actually longer than.
Yeah, because the cards that don't get picked enough slow you down. That's exactly right. Yeah, that's exactly what's happening. Okay, good. So now I'll go to how you would prove something like this. And okay, so the tools are, you go through the spectrum of the transition matrix, okay? So back to this matrix where each entry was the probability of moving from X to Y. Nicely enough, P is a symmetric matrix. So we have real eigenvalues, and we have already seen in Amel's talk that we can say some things about these eigenvalues. So there are 2n factorial of them, and they are between -1 and 1. The very first one is equal to 1.
The mixing time is b minus 1 n log 2n, is it important that it's log?
No. I mean, it says that you have 2n cards. That's all. But
But for the cutoff, you still have the C, right?
Yeah.
it's captured in the window, the 2 term. But yeah, I should have written the 2. I should have written 2. This is a struggle. This is a struggle of me thinking of this in terms of n cards, and then you have 1/2 n, 1/2 n, and us deciding last week to turn everything to 2n, and so I need to get used to our new notation. But thank you. Yes, I'll have a few of those during the talk.
Is it really, I mean, like, if your C is fixed, do you actually get 0?
For
or you just get some-
cutoff, I did say that C will be going to 0, but
Well, but then with an n log n somehow, right? I mean, here you have an n. I mean, for cutoff, usually you would write C n log n, I guess, and then send C to 0. So it's a similar, a small window on the same scale. So here you put on a slightly different scale because you put an n.
Yes, yes, and it will be n or log n.
But isn't the smallest eigenvalue going to be 1/n?
No. No. Wait, the smallest is or the biggest, because I don't care for the biggest one, which eigenvalue do you care for?
Right, yeah.
Yeah,
I mean, like,
no.
yeah,
It's
exactly,
gonna be
yeah.
very close to one.
Yeah, but
So,
what's the size of it?
it is gonna be of order 1/n with a constant depending on b.
Right, but
Yeah.
then doesn't that precisely tell you that the size of the window is going to be n? So if you fix a constant.
Okay, so you want the sharp window, and I'm telling you,
I'm just saying what you're stating here, because you put it, you're moving by n, but n is actually the size of the window, so you're not out of the window yet. So if you're at 0, you should.
the main term is here, so this drop will happen at n log n times the constant, and then you will move n steps forward to get small, and if you move n steps before, you'll be big. That's what I'm stating. So I'm not sure what the, yeah,
Because you wrote equal to 0. That's it.
but there is a limit. Okay.
Okay.
In this case, I believe so, yes. But you know what? Again, because we're writing the paper,
Okay.
I will do this to make everyone happy, but I believe that, no. I see what you're saying. No. Martin, I see what you're saying. We really need to put this to make you happy. Yes, I see what you're saying. This is a question of limit profiles. I agree completely. So I would have liked to write that this thing is less than e to the minus c, and that this is 1 minus e to the minus c. So I think we would be okay. So I should have written this and now we're good, right? That's what you were complaining about, and now I understand. I thought it was going to here and not here. Good, perfect. And in fact, that's where I would like to take it at the end. We haven't done that yet, but if I remove this, so I shouldn't have removed this, I shouldn't have omitted it, I do want to be able to say what type of function I get. That would be my ideal goal. That's the limit profile, but that's a new subject in card shuffling and might be hard, but anyway, I like it. So how would you prove part A of this? Okay, good. Well, you do Cauchy's bars basically. And you rewrite the L2 norm nicely. And it turns out that the L2 norm is given by the eigenvalues. And so now, so we are on a Cayley graph, so the eigenfunctions don't play any role. That's why you don't see them. But now this means that we need to find the eigenvalues of this transition matrix and then analyze this sum and see how it behaves. And that's where representation theory comes in to help. You know, when you need to diagonalize a 2n factorial by a 2n factorial matrix, then you need some rules. Okay, so going back to Diaconis and Shahshahani. So case P1. It is crucial that in their case, all transpositions get the same weight. So the generating set of the Cayley graph you walk in is a conjugacy class, and you can use Shor's lemma, some heavy machine uniform representation theory. So what they found is that if you take a partition of 2n, so what is that? That is a vector, finite many parts, such that lambda I is bigger than lambda I plus 1 is positive, and the sum of lambda i's is equal to 2n. Oh, actually, no. Okay, so that's what the partition of n is, 2n. Then just to give you the formula, because we're going to use it again and again, we can think of the partition in terms of a diagram. So if the partition, for example, is 3, 2, that's a partition of, well, 5. So 3, 2, 1. Then we can view 3 as 3 boxes, then 2 boxes, and then one box. And that's the same type of presentation. And the main statistic that appears in the eigenvalues for b equals 1 and for the general case is the diagonal index of such a partition, which is that each box now has coordinates. So 1, 2, 3, 1, 2, 3. So this is the box 1, 2, for example. And what you do is you take the differences of these coordinates for every box. So if I take differences, the diagonal always has 0, this has 1, this has 2, this has -1, and this has -2, and you add this up, and it's 0 in this case, just to see what the statistic is. So the eigenvalues they found are the following. So so for every partition of 2n, this is the corresponding eigenvalue. And okay, with multiplicity, I might discuss multiplicities at the end. The dimension of the representation squared, whatever that is, I might come back to it later. So we want to get an expression, a very nice expression. These are the eigenvalues of random transpositions. We want to get something as nice for the biased ones. Good. Okay. So before going there, I want to just make it clear that it's not every day that we can diagonalize a 2n factorial by 2n factorial matrix. As I said, it was special that this was the conjugacy class. A few more examples. Star transpositions by Plato or the Leaves waves. So we transpose the top card with a uniformly random card. That's what they did. Again, using representation theory. Diker and Sayola diagonalize random to random. So you pick a card that's random, remove it from the deck, put it at a random position. They introduced a whole new technique, which for card shuffling was quite a breakthrough. And then something similar to this is the one-sided transpositions. Batecomer and Matore. So as far as card shuffling is concerned, that's what I know in terms of diagonalizing transition matrices. And with this new technique, there might be more. For example, Samira, if I am a student, will do case star transpositions. She's doing it right now. So there is something to be said that there has been something like 40 years since Diaconis and Shahshahani resolved, and still diagonalizing these matrices is hard. So for our case, the eigenvalues that Alan and I found have the following formula. So let's set A to be 2 minus B. The probability of staying fixed is something like this. And then we get a term that depends on A and B, so B and 2 minus B, a partition lambda of 2n, a partition mu of n, and a partition mu of n. So we have 3 terms. And the formula for this expression is given hopefully by this. I say hopefully because I'm just memorizing it. So the same statistic, this diagonal index that appeared in random transpositions, but now with 3 different partitions, 2 of n and 1 of 2n. Notice that if A equals B equals 1, these terms disappear. This is 1, and we retrieve hopefully the old result of Diaconis and Shahshahani. Yes, the multiplicity, sorry. Yes. Okay. I might say more at the end, but let me write it down for people who at least know. With multiplicities, so P lambda, the dimension of that module lambda, F mu, and then the little wood Richardson coefficients. I will see if I have time to define those. It's not the most essential thing to do right now. What I want to do is actually give you my simplistic idea of why this should be true. I might have oversimplified, but I'm quite proud that I might be able to tell you how this works without saying too much about representation theory. So instead of thinking of the transition matrix, one could think of the group algebra element, which is, say, the probability that you start from the identity and you land at, say, transposition xy. We can allow x to be equal y so that we also have the identity here. And we can decompose this. So let me remind you that A was the first, I just erased it. A were the first n cards, B are the next n cards. And so we can say, okay, what if both x and y are in A? So this happens with probability. I think A and B should be swapped, whatever, B squared over n squared. Or 2n squared, it doesn't matter. As I said, now the numbers don't be too cool with me. What if they're both in B? I'm trying to communicate the idea, that's all. What if they're both in B? Then we have a squared over 2n squared xy. And what if one of them is in A and one of them in B? Bear with me. So AB over n squared. And so the whole point is that this is a random transposition. And so the weights can go out. They don't depend on the sum. And you retrieve the group algebra element for random transpositions on n cards here. On n cards here. And here you get the term, you can cheat and notice, so you can express it in terms of the other terms. For the last term, for this one, cheat and note that if we remove all weights, so both in A plus both in B plus twice, whatever. That's random transposition on 2n cards. Random transpositions on 2n cards. So you can solve in terms of this, random transpositions of 2n cards minus random transpositions of n cards, random transpositions of n cards. All this to say that you can separately diagonalize these three, and these three happen to somehow provide some use. So somehow you can fully diagonalize it this way, and the expression you get over there really comes from taking the eigenvalue of this, and the eigenvalue of this, which you can express in terms of these guys, and retrieve this. Now, to get the multiplicities, we have to get our hands dirty, and really to make this all more rigorous, we use only this fact from representation theory. I'll write it down and then not mention representation theory anymore, that the spec module with respect to S lambda, more space. If we restrict it, so you look at it as a representation of S2n. If you restrict it on Sn cross Sn, we know exactly how this decomposes. And that is exactly the S mu tensor S mu with the little Richardson coefficients. And I will not say more than that, but just so that you see where the multiplicities come from. Okay, so that is what I want to say in terms of diagonalizing. in terms of the analysis, what people use, so just to give one heuristic, to determine where cutoff occurs, what shall I write? Not the formula. Okay, this one. So the heuristic is that you always take the n-1 dimensional representation, so the partition 2n minus 1, 1 in this case. So response to this. And you compute all the eigenvalues in here, raise them to the 2t times the multiplicity, and add them up. And these are the ones to give away where cutoff happens. That is a heuristic, but in case of shuffling with transpositions, because of Aldous conjectures, something that was proven by Caputo, Liggett, and Richtmeier, it always works for transpositions, but for general shuffles, it's not always true. So one would have to go and say, okay, the possibilities for mu needs to live inside lambda for these Littlewood-Richardson coefficients to work. So we just have 4 cases. Mu needs to be either this or the trivial, because it needs to live inside this shape. And similarly, mu, so it's either this or the trivial. And here as well. And so you take the formula for each one of those, compute the eigenvalues, compute the multiplicity. The multiplicity is not that big in this case, and that's how you can guess the B inverse n log 2n. But it is a computation that I usually show in less complicated shuffles like random transpositions. But at this time, I think I'd rather stop and go for dinner. Thank you so much.
Any questions?
Alex.
Maybe this is kind of an obvious question, but if I wanted to do 3 different categories or 5 or whatever, is that easier or hard? Is that harder? Or?
That is exactly what I want my graduate students to do. So I'm saying away because I want them to do it, but you will need to study this decomposition. Okay, so once they do that and they get something nice, then hopefully things will work. So future project.
Do you have a guess for what the
coefficient?
yeah.
It could be the minimum of the 3, but I wouldn't be surprised if I'm wrong.
What if the blocks are not the same size?
Yeah, very good. Everything I said, you can do it for general A and A complement. You can totally diagonalize. We did not do the mixing time because it's daunting. Like the formula gets a little bit tricky. We just finished the case of equal packs, and also the positions don't matter. It could be any positions in the deck. But if we get brave, we might try it because it's cool to see what happens in mixing. Like especially if say, A has size 3 and the rest has n minus 3, then is there cutoff? What's happening? I don't know. It's an excellent question.
Any questions? Evita? What does it mean? Round minus nine. Maybe.